presentation. Before we get sort of formally in the process, a couple announcements. One is remind people to stay here for the business meeting. Is that loud enough? Yes? Can you hear me in the back? The guy taking a picture? Okay. So after the symposium, we'll have a 10-minute meeting for the society, so I encourage everybody to stay here. Also, even more important, the reception at 5:30 at main court. You don't want to miss it because Debra is paying, right? But you might come for a while.
Oh, for the videos.
Okay, I'll say
you could just hold that. Lip syncing? Yeah, with the video, we'll hear you. There, let me see here, I can get it for you. Flip it for you. I got it. There we go. Thank you. I appreciate this. Okay, my goodness, that's loud. So now I'm tethered to this damn thing. Okay, so I can't run around. Again, welcome everybody. So as I mentioned, two brief announcements. Stay around for the meeting at the end of the symposium, and the other one, that 5:30 reception at main court. So we're now ready to rock and roll. So it's really my great pleasure to chair this symposium in honor of Debra Rolison and Lane Baker, the winners of the C.N. Reilley and Young Punk or Young Investigator Award from the Society of Electroanalytical Chemistry. I'll just say a few words about Debra, and where's Dick? Do you want to say something about Lane? You know, when we, after the intermission, we'll do the presentation, so you can do a few words about Lane. So I'll be very brief in my remarks. We don't want to impose on the time constraints here. So it really is my great pleasure that she needs an introduction here, right? Debra Rolison, the winner of this year's Charles Norwood, in case you were wondering what the CN stands for, Reilley Award, who was a towering intellect and contributor to the general field of analytical chemistry. As he would put it, analytical chemistry is what analytical chemists do. So you do the math, right? And in addition, of particular relevance to this crowd in electrochemistry. So Debra got her bachelor's degree at Florida International, as I recall. No, Florida Atlantic, working with Frank Schultz as undergraduate researcher. From there, she went to the University of North Carolina at Chapel Hill, where we met years ago. So I've known, typically when people ask me how long I've known Debra, I says, longer than I should acknowledge, but rough cut numbers, 35 years. When in graduate school, it was clear that she was a person of tremendous intellect and forcefulness that she has kept to this day. After finishing Chapel Hill, she went to the Naval Research Lab, where she had sort of a meteoric rise to the ranks, and she is now director of the head advanced electrochemical materials section at the NRL. Is that correct? Good enough for government work, literally, right? So if one were to define Debra's contributions, I can't do this, would be making us think in different ways about electrochemical interfaces, that nothing is not the same as absence of. There is a place for nothingness, there's a place for assembling architectures in electrochemical systems to address, all sorts of things, be it catalysis, be it, energy storage in batteries, supercaps, and how do we take the concepts that we have learned and sort of spin them in a different context to achieve particular functionalities. Of particular note has been work on sort of three-dimensional batteries and electrical energy storage materials, electrocatalysis, basically all areas that are now, all of a sudden, let's say, popular within the funding schemes. Debra has been sort of paving the way for the way we think about electrochemical interfaces. The other aspect, and I'll read from the letter because when I wrote this is all the letter, kiddo. So the other aspect that I wanted to address is Debra's commitment to education. So I'll just simply read the last two paragraphs. So in addition to her great scientific contributions and professional service, Dr. Rolison has been an indefatigable voice to increase the participation of women and other underrepresented groups in science and engineering. She writes and lectures with the same passion she has for her science, and her efforts, in fact, have inspired many and affected policies. While she has at times been criticized and her career has been affected by her forcefulness and diligence in these issues, her commitment remains unshaken. How many of us would have taken such principled positions? And my guess is not many. I finish. In summary, Debra Rolison epitomizes a passion for science and a search for social justice that are rare in our times. She is truly most deserving of the C.N. Reilley Award. Parenthetically, having known Professor Reilley, I am certain that he would be proud of her himself. In electroanalytical chemistry, Debra is a real gem as a scientist, as an individual, and I, in the strongest and enthusiastic terms, nominate her. And with that, I give you Debra. But before we do that, Jonah will give you the secret handshake. Watch your feet.
Watch my feet.
There we go.
There we go. Very good. So this is the 2012 Award presented to Debra Rolison to recognize her outstanding contributions to electroanalytical chemistry, sponsored by BAS. Thank you all for coming. We're going to have a great afternoon of out there analytical, electro, and its science. My thanks as well to the Society for Electroanalytical Chemistry for acknowledging me as the 29th awardee in a long line of supremely distinguished electrochemists, and BASI for firstly endowing the award and then keeping it up and running. And many people feel I don't do much analytical chemistry. But what we never forget is we always do analytical chemistry. And I want to tell you how electroanalysis is key to understanding technologically relevant nanomaterials. Tito's already given us this famous Reilley quote. So what this analytical chemist does is materials chemistry. And when I started doing hands-on electrochemistry as an undergraduate with Frank Schultz at Florida Atlantic, Frank cracked me up one day. He said, when analytical chemists are handed an unknown, they have two questions. What is in it, and how much of it is there? Which, of course, would be absolutely frustrating to somebody who brings you an unknown and wants to know what's in it and how much is there. That's what you're analyzing it for. But Frank's point was that the problem is how you approach it. You need to know a little bit about what you're analyzing, otherwise it's too big a phase space. And Charlie made that point when I was a graduate student at Chapel Hill, that you can be extremely versed in a technique. But you also, as an analytical chemist, have to ask, what does the problem need? And then bring whatever the problem needs to that analysis. So I would say any experimental chemist who isn't a good analytical chemist doesn't know what the results of his or her experiment is. And when I ran the 2001 Gordon Conference on Electrochemistry, I reminded our attendees that when charge moves, it's electrochemistry, and in chemistry, charge is always moving. So, again, huge phase space. I like to say Jeff Long and I, former postdoc, longtime staff colleague now, we run the Navy's nanoarchitectural firm with some great postdocs converted to staff. Megan Sasson is here in the second row, our most recent hire, undergraduate scientists, and contract researchers. And we pick architecture as our design paradigm because we want to be able to bring multiple function into an object. And biology is known forever that to bring food in, waste out, reactant in, product out, you've got to have a pathway to move. You've got to vascularize. And that is not exactly a periodic, if you will, path to move molecules. So we feel that one must think like an architect to put nanoscale building blocks into something that is, just as this building is, mostly nothing. And the nothing is the key part of the functionality. And if you're going to be an architect, you get to decide what I like to be regular, rectilinear, periodic, and have great function, such as the I.M. Pei Johnson Museum of Art at Cornell, or functionally whimsical, like Santiago Calatrava, where you don't see right angles. Rectilinearity is not part of his design portfolio. But when you enter the Milwaukee Art Museum, you see why, again, architecture always brings the same thing. Mostly nothing and interconnected to other parts of the building. You need that to do anything. And we don't want to take a little bit of nano and arrange it in XYZ space. We'd like everything to do itself, but this is not what anybody would call self-assembly. It's self-construction, and we do that through sol-gel science. Start doing SN2 chemistry, acido-base catalyzed, to create a metal hydroxyl, in this case a silanol. They then in turn do more SN2 chemistry on other metal hydroxyls, and before you know it, in the liquid phase at room temperature, you've got a metal oxide. No heat, no beat. And if you've controlled your kinetics appropriately, these little nanometric bits dispersed in the liquid, the definition of a sol, bond to one another covalently to form the gel. And if you put a pure fluid in that pore and go supercritical, as was recognized in the 1930s, you have all that interconnected volume interconnected with air, thus the aerogel. Now, of course, you have to go into something that can be pressurized and raise the temperature and get above the supercritical point. We use liquid CO2, very simple reactor. Nobody dies if there's a leak. We've taught high school students how to make aerogels. We've taught undergrads. We've taught physicists. It's that easy. Sabbatical faculty have learned to do this, yes. Many out of the lab for a long time. The canonical cartoon for an aerogel are these nanometric bits of whatever your oxide or carbon species is, covalently bonded, filling a volume where most of the space is open on the order of tens of nanometers, or mesopores. Now, some people really would like to avoid having to pressurize a reaction vehicle, so you can also put a non-polar organic, low surface tension into the pure fluid and just dry that, raise the temperature a bit. Voila, you have a ambiently pressure-dried gel where you still have kept the porosity interconnected in 3D. We call those ambigels. The important point is, unlike most templated porous objects, this retains its structure from nanometers to meter length scales. It's very hard to take templated porosity and retain any registry much past 5 or 10 microns. And anywhere you see the bouncing gold ball, a chemist can come in and change the function. So to summarize some of the things that a structure like this walks in the door with is as much surface area as you can get based on the molecular weight of your oxide. So for silica, you're over 1 million per centimeter in your surface to volume ratio. That's amplifying what you care about if you're a surface scientist, the nature of that surface. The plumbing is stayed 3D, so you get very close to open medium diffusion rates. The particles are bonded. So if you're moving charge, that's important. That does not introduce junctions or impedances. So it's mostly nothing, which is why we like to think we're architects. It is not a photo op. This has not got that periodic porosity that can get you into science. But this shows you the large size of the void space and why it's so easy to get molecules in and out of the structure. This is only 15% the density of silica. So we're looking very deeply into this structure using the high-resolution SEM. And because of those bouncing gold balls, you can introduce whatever property you want for your end application. And today, I'll focus on electrical conductivity. So, huge amplification of surface properties, making your analysis much, much easier. So one of the systems we, shall we say, solved just by making it in aerogel form was the quixotic thing known as electrochemical drying. People working with photoanodes of titania, getting the particle size smaller, found that if they could poise these structures, these electrodes at very negative potentials and dry non-aqueous electrolyte, it became more hydrophobic with time at potential. That's called electrochemical drying. That helps improve your photoanodic performance. Titania as an aerogel is not very mechanically robust, so we worked with the powder but re-glued it back with silica sol and then dried the composite as an aerogel, heated it to take the titania to anatase. And now you have almost a monolayer surface coverage of titanols. Those are normally defect traps that usually plummets your photoanodic character. Very high surface area, but we've got the architecture. Wired nanoparticles, electrolyte-filled 3D free volume. And just with one scan in dry non-aqueous electrolyte, every electrochemist in this room knows what has happened. Here's the first scan where you're passing a fair bit of charge at very negative potentials. Second scan, there's far less charge being stored at that interface. You've dried it out. It is now hydrophobic. You don't have the same structure of water that is always coming in with those titanols being present. So what's going on is, back to sol-gel chemistry, it's condensation because we've electrogenerated hydroxide by going so negative, and the hydroxide is coming from the water that is coming in with those titanols. So if you look at those general reactions for sol-gel chemistry, at the end of the day, you come from a lot of titanol to something that looks back to perfect titanium 4 oxide. That's why it dries out. Now, we recognize this and publish it at the exact same time that Fujishima and Watanabe's group did, and of course, they're the ones who really started first working with photoanodes and titania back in the 70s. It was obvious with the aerogel. It took a little bit more time with other forms of titanium. But you can undo sol-gel chemistry, particularly if you get too much water in the system. So we also recognize that we could electrogenerate, shall we say, a better reactant. In this case, the anion radical form of isopropanol, the isopropyl radical. And again, you completely make this very hydrophobic, and the performance enhancement you get. Dark photocurrent, we're now in water with sodium hydroxide. This has not been modified, that's the dark current. This has not been modified, that's with light. But you put the isopropanol grafted onto the titanols, healing those defects, you double the photocurrent. So again, the kind of information we got from analyzing titanol-rich titania immediately allowed us to look at a different way to improve this system as a photoanode. A second approach with manganese oxide, now dried as the Ambigel. We've got a little fire plug of a monolith of burnasite-like MnO2. These are the MnO6 octahedra arranged in planes. Every now and then in the transmission microscope, you can see the lamellar layers. Sodium and water between the layers. This is about a 0.7 millimeter monolith, and we're going to make solid state electrical measurements with platinum top and bottom electrode contacts. We're equilibrating with different concentrations of water or relative humidity at ambient temperature, and when we're as dry as we can get it, it's a beautiful arc. And the minute you start introducing relative humidity, 11, 29, 58, 75, 84%, it gets much less resistive. You lower the impedance. And that, of course, is the signature that you're moving protons. But the other thing that shows up here is a linear element, the Warburg. Now, you usually expect to see a Warburg in a 3D isotropic, for instance, a liquid electrolyte. If you blow those data up, so we can't show the drier data here because they're closing over here, you can see the Warburg. You can do that analysis with that circuit. The most general form of the Warburg equation is the frequency to the minus beta. And in the 3D, like a liquid electrolyte, that's 1/2. That gives us the Warburg slope of 45 degrees we know and love. But there's also the Warburg coefficient, which has all the parameters we also know and love. And it's the charge on the carrier, the Faraday, the area through which the medium is conducting, the concentration of the carriers, their diffusion coefficient. And if you are working in dilute conditions, millimolar or lower, you can pull out valid properties from that Warburg fit. And the fit we wanted to pull out was to look at the limiting resistance at the end of the Warburg, so this is going down to 10th hertz, using the Warburg coefficient after the fit, and actually calculating the length the proton was moving. So as these different relative humidities are equilibrated with that monolith, and we fit the data, well, we fit the criterion because we're micromolar. The real surprise was what was the length of diffusion for that proton. Macroscopic, 0.3 millimeters, which means it's running the length of that monolith with impunity, even though this is mostly nothing. So the formalism is valid, the diffusion length is huge, and as your eye is already telling you, that's not a 45-degree slope. And the suppression of that, we actually can pack out the dimensionality of the proton transport, and it's 1.6 D. This object is about 2.4, 2.5 dimensional. Aerogels are fractal. So the proton is, of course, trying to find the shortest path it can between the two electrodes. Not quite 1D, but definitely not the dimensionality of the scaffold. So we've got a proton wire at long lengths because of the architecture. If we have this monolith and chunk it up, as many people would if they had a nanopowder and wanted to do a sensor to humidity, they would form a particulate film. And when we chunk this up, we drop the sensitivity to relative humidity by a factor of 15, right where it is in the literature for electrolytic manganese dioxide. So we can make or break the proton wire based on what we do with that size of that aerogel. And when we're monolithic, we chemisorb water from the vapor phase. Ultimately, we'll build up a sheath of water around the scaffold of the oxide, and that's why it's just running back and forth with impunity. But you break it by introducing impedance junctions. It may be moving quite rapidly through here, but it still has to hand off particle to particle. So if you want to do any kind of conductometric sensor, you would like not to break the wires between points in the film. So you should be able to enhance ion transport. This should help us improve the mobility of ions in electrochemical power that we care about. Of course, we can change our sensitivity to humidity. And I've put the proton here. Well, this makes perfect sense. It's easy to imagine a sheath of water adsorbing at these oxide scaffolds. But an oxide ion? Well, when we made the gadolinium 3+ doped cerium 4 oxide aerogel, which you would be of interest in a solid oxide fuel cell, has to operate at 600 degrees C. We found that the gadolinium did what it should do, introduced anion vacancy, so it was much less resistive than the pure ceria aerogel. And we had an architectural difference now. The aerogel was much less resistive than the ambigel. And when you looked at the impedance at 600 degrees C in an oxygen atmosphere, we get a Warburg back. So again, we've got a long path for the oxide ions. We could back out the activation energy for transport of oxide ion in the system. That is, in essence, the single crystal value for gadolinium-doped ceria, although this is nobody's idea of a single crystal. Again, the long transport, again, about 1.6 dimensional. So, let's go back to grad school. Most of us answer enough questions to get our PhD, but there's usually some persistent life questions based on our PhD work. That's why George Whitesides travels the world asking everyone he meets if they can explain magnetism to him. And I worked on ruthenia first with Royce, showing that in non-aqueous media, the ruthenium dioxide as a working electrode was almost up to platinum standards in terms of the rapidity of its electron transfer rates. So I wanted to make a ruthenia aerogel, and that's essentially impossible. So we piggybacked on a literature way to make titanium aerogels, as you've already seen, and doped in ruthenia by just having a ruthenia component present during the gelation. So the electrical character of pure titanium aerogel is pretty resistive, but just as I showed you for the MnO2, if there's water in the atmosphere, it's less resistive, helping to show that titanium is a bad, but it is a proton conductor. If you get above a percolation threshold of ruthenium dioxide, it's markedly less resistive. So ambient air is this blue curve here, and at about a kiloohm centimeter, it's as good as Nafion for moving protons. That was not expected for ruthenia. You dry it out, which is this pink-red curve here. You become less conductive, more resistive. You give it more water, it gets less resistive. So again, the proton is moving in this system. And that was of importance to us because we were trying to also do work funded by DARPA to understand platinum ruthenium catalysts used in direct methanol fuel cells. Now, the folklore, the wisdom was that these blacks, although nanoscopic, were alloys. All that work had been worked with bulk alloys, and people understood the methanol oxidation mechanism fairly well. But once we started analyzing these real materials, we found that there was barely any alloy there. It was platinum with a lot of oxidized forms of ruthenium. And so if you electroanalyze that, do a Tafel plot, the equilibrium value for the methanol is about here. Here's where the Tafel slope for the alloy is going to come out. So this has been reduced in hydrogen to make it like an alloy. What came in out of the bottle, which was an absolute mess, gives you the highest activity. It's 250 times more active than the nanoscale alloy. And the ruthenium hydroxylated speciation is critical to achieving that activity. So if you reduce it in hydrogen, you can indeed see lattice fringes that map onto a platinum-ruthenium alloy. We do not phase separate the HCP form of ruthenium, but once you've given it a chance for thermodynamics to do what it wants to do with a galvanic couple, you form hydrous ruthenium oxide that is laying on top of a platinum-rich inner core. It's disordered, it's got breaks in it. That's why the methanol can get down to the platinum, and the electron-proton conductivity of the ruthenia does the rest of the work. So we've often in our literature thought of RuO2, ruthenium dioxide, ruthenia, as sort of a homogeneous material. When a single crystal, it is 22,000 Siemens per centimeter. It's a great metallic-like electron conductor, but most people don't use it. It's a platinum group metal. So when you chunk it up, you don't have proton conductivity. You've got high electron conductivity. It's about 100 Siemens per centimeter, and that has technological uses in thick film resistors and barrier layers in memory. In the 70s and 80s, it was recognized, well, even earlier, the dimensionally stable anode has a rather beaten up form of ruthenium dioxide as part of that anode that's oxidizing chloride to chlorine. Same conductivity and ability to store some charge at the surface. Conway and Trasadi in particular focused on that in the 80s. But the catalytic form of RuO2 that we found in direct methanol when you just have pure hydrous ruthenium oxide is the world's champion for charge storage, over 720 farads per gram. And that's per gram of ruthenium dioxide, which is heavy, unlike the 80, 90, 100 farads per gram you get with carbon, which is light. So this system behaves chemically completely different relative to these dehydrated crystalline forms. These can be dissolved in HF. You have to go to a sodium flux with this very hydrous disordered form, and you've got bulk proton conductivity. So we did some atomic pair distribution functional analysis of the structure in collaboration with Takeshi Agami then at Penn and Wojciech Domowski, his senior staff scientist. And what came out is that regardless of how much water is in the hydrous ruthenium, down to 2 moles of water per RuO2, there is always a true rutile crystalline core. But it's only 1 or 2 nanometers, which is why you don't see it by X-ray diffraction. And then as you put in, shall we say, more order, those regions get larger, and the proton conductive interfaces get smaller. And that finally, well, I call this the inorganic analog to diblock copolymers, because you're putting the most important function, moving the protons and the electrons, at a very thin interface between the two. And that finally explained why, when you were working with hydrous ruthenium oxide, either very water-rich or very dehydrated, you had a volcano plot in terms of how much charge was starred. So here we've got a tie line. These two structures are storing the same amount of charge, but they have different fractions of the ruthenia versus the proton-conducting hydrous phase. Well, we still wanted to get the ruthenium used, but a little bit less of it than bulk, because it is a platinum group metal, and worked out a way to wire 2 nanometer high RuO2 webs throughout a silica aerogel. Published that in Nature in 2000. Took more than a week to make, and it was a total pain. So Chris Chervin adapted the protocol, but now on the benchtop, out of PET ether, sub-0 degree temperatures, but used quartz silica gas diffusion paper. What comes out is black, and it's conductive, but not greatly conductive, same thing we saw with the aerogel. But as you heat it in air, it just improves its conductivity up to 3 orders of magnitude, as long as you don't go much past 220. And wherever you cool down at, it retains whatever the conductivity was there. So now we have a sort of a nanometric form of RuO2 with 3 orders of magnitude delta in its conductivity, which of course the physicists love, because they can go in and ask all sorts of fundamental electron-phonon physics questions. In the high-res SEM, you see like packed sand at the beach, very small nucleates of the RuO2, and every now and then we see a break in the film so we can actually see down to the silica fiber and get a really high-quality image. But we really wanted to know how thick this nanoshell was. By TEM, on the very thinnest fibers, you can see something that's about 2 to 3 nanometers thick. But again, electrochemistry turned out to be the better way to do this. Half-molar sulfuric acid, the ruthenia wrapped silica fibers in the paper, and this is its current voltage curve. It's a beautiful charge storage capacitor. And we're going between 2 and 100 millivolts per second, and it's not changing very much as a function of scan rate. So we applied the formalism that Trosati taught us in 1990, where you plot 1 over the square root of scan rate and extrapolate that to infinite scan rate, because then you're only looking at the charge that is at the outermost surface. And when we do that, we see 90%. This extrapolated number is 90% of what we see at the 2 millivolts per second, which means this film is all surface. And if you do some calculations based on the unit cell of rutile, a 3 nanometer bit of rutile would have 63% of the units at the surface, 2 nanometers, 94%. So again, this falls in that sort of 2 to 3 nanometer ballpark. And when we go into a non-aqueous electrolyte where we can't insert protons, use something like tetrabutyl ammonium perchlorate, then we back out 90 square meters per gram for that ruthenia, again putting it in about a 3 nanometer thickness range. So an extremely limited amount of ruthenia is giving us some really nice properties with respect to the electrochemistry and charge storage. So let's look at its charge storage as a function of that heating curve I talked about. So heating at 100 in air improves the conductivity to about 0.2 of a Siemens per centimeter, and you can see it's kind of resistive, so we didn't even try to back out how much charge was stored in there. At 150, you're back to perfection. This is what it looks like in SEM, that packed, fine pebble, monolithic sort of coating. At 200, it doesn't change. There's maybe a little back off in how much charge is stored. There's actually improvement in the conductivity from 150 to 200, from half a Siemens per centimeter to 830 millisiemens per centimeter. But once we go to 250, you can see we're ripening the particles, we're changing the morphology, and we've lost a lot of the charge stored. And at 300, we actually have so little ruthenia there, the particles ripen to the point where we can actually see bare silica in the microscopy, lose the conductivity, lose the charge storage. So this system does what it kind of does in bulk, in the sense that you don't want to be too crystalline to store the maximum amount of charge, and you don't want to be too low conductivity to store the maximum amount of charge. There is a sweet spot that for this size of particle is sitting at around 150 degrees calcination in air. So we wanted to ask how stable was so little ruthenia on the paper as a function of atmosphere, using the pseudocapacitance, the charge stored in aqueous acid, as our metric. And if we expose that ruthenia shell on the paper to air, hydrated air, argon, water sparged argon, methanol or water methanol vapors, there's no change in the capacitance. But give it some hydrogen and you reduce some of the ruthenium to metal. So it's not going to be stable in hydrogen atmospheres. It's helped a little bit by having water present. It doesn't get quite as metallic, but we're not going to be able to use this in a hydrogen fuel cell at the anode. So let's not use it in a hydrogen fuel cell as the anode. So Jeremy Pittcon, in collaboration with Mike Pomfret, adapted Reg Penner's electrodeposition approach to take skins of the ruthenia, now on a planar surface, titanium coupons, and deposited either about 4 nanometer to 5 nanometer bits of platinum, or extremely small, about 2 nanometer bits that you can see in a high quality image of this micrograph. Now, in aqueous perchlorate, with just the ruthenia titania, you see a lot of capacitance, so you haven't lost that by putting it on the titanium support. And once the platinum is there, you really, it's not a well-defined hydrogen absorption and desorption, but you know the platinum's there because you can see the oxide stripping peak. And because there's 2 particle sizes there, we actually get 2 peaks for the CO stripping, and the 2 nanometer has one of the lowest CO stripping potentials out there. And that, we believe, is because it is so closely nestled to the ruthenia. So now let's add some methanol. Here's the curve you already seen before, that nanometric bits of platinum dispersed on the nanoskin of ruthenia supported on titanium. With just the ruthenia and methanol, there's mostly capacitance, and then the ruthenia can do some oxidation of methanol, but you have to go to extreme oxidizing potentials. With the platinum, it doesn't change all that much, but it does change. Part of the problem is we have so much pseudocapacitance here. So if you background subtract that, you get the classic hysteretical voltammogram you expect for methanol at platinum. Forward-going sweep, return sweep. But now the potential is as good as it gets. 0.64 volts versus the relative hydrogen electrode. So we are very encouraged by this ability to pretty much size the platinum at the same size of that electron-proton conducting ruthenia. And Chris Chervin and Jeremy are now adapting this to titanium mesh to see if this is going to be a practical electrolyzer electrode. But while we've got ruthenia on planes, let's put it on a transparent window. And we can also repeat these deposition procedures. So we can put down 1 layer, 2 layers, 3 layers. So here's an example of 1 layer, now a nanoskin, not a nano shell, on silica, a fused silica or quartz. You can see it darkens at 3 layers, but is still transparent. Darkens at 5, but is still, you can get some light through it. And as we have studied this over an extremely long wavelength range, it's broadband flat, from the terahertz to the ultraviolet. That's very hard to accomplish with almost any other electrically conductive, transparent window. And so Jeff could take calcium fluoride coated with a skin of the RuO2 and electrochemically deposit Prussian blue, and on our carry, which goes from ultraviolet to near IR, see the intervalent charge transfer, which gives the color, see the D to D star for the iron in the ultraviolet, and see the nitrile stretch in the near IR. We're actually pushing this out to microwave now. So we now have a pretty good conductor that is, as like we say, DC to daylight transparent. And why are we interested in that? Well, some of the other projects we do have to do with making better battery materials out of very cheap, non-toxic, non-strategic things. So rust is nobody's idea of an insertion electrode for lithium, as you can see in this charge-discharge plot. But if we swap out some of the iron for molybdenum-6, you can immediately see how much we've improved the capacity and the capacity potential, which massively improves the energy density. The Moly-6 substitution creates proton-stabilized cation vacancies. We verified that by a number of methods. We're getting both a more positive voltage, which improves energy, and 4 to 5 times more capacity relative to the host iron oxide rust structure. So you get a double whammy from that. It's about a factor of 7 more capacitive in terms of energy density than the iron oxide. And these are actually coming from classic coin cell measurements. This is not flooded electrolyte measurements. But we don't know where the color center is. People know that all of these insertion oxides are electrochromic. They're usually very ugly electrochromic materials. But that's telling you something about the electronic state of the metal centers as it's charging and discharging these lithium ions. When you have anion vacancies, such as in vanadium, you often see a shift towards the near IR, but nobody has been willing to calculate for us where the color center would be for the insertion metal near a cation vacancy. So we're just going to have to go look for it ourselves. So in this example, Jeff Long took the ruthenia deposited on fused silica, so that's the window, electrodeposited electrolytic MnO2, which is what's running this laser pointer, and then took it an in situ spectrum, subtracted the background, and you can see there's information in the ultraviolet. And this is a region you just generally don't and can't study with these metal oxides. It's known to be more color-based when it's manganese 4, and it decolorizes as you reduce it to form manganese 3, and the lithium or other cation would insert into the structure. So this is what it looks like doing some very early spectroelectrochemistry in this system. So at plus 0.1, you've made manganese 3, and it's colorless. As you take the potential positive and start converting that to manganese 4 plus, it colors. Normally you would be monitoring the color at about 500, so you can see that march up as we get back towards the color center of manganese 4. But look at all the information in the ultraviolet. So now we can study this as a function of how defective is that oxide, what's happening to the color center in a way we never could before. So I'd like to thank everyone again for coming, BASI for sponsoring this award, but I want to harken back to 1978. So you saw me in my graduate school era working on Ruthenia, Mickey Mouse shirt and all. That really was a bit of a statement on the PhD projects. But in 1978, Royce chaired the Gordon Research Conference on Electrochemistry. So here you can see the outstanding triumvirate Tito and Henry and others and I experienced when we were at Chapel Hill in the 70s. Here's Charlie Reilley right here, front and center. Dick Buck, Royce Murray. Royce was chair. And when I arrived at Chapel Hill in 1975, and I had these three great electrochemists, C.N. Reilley, R.P. Buck, R.W. Murray, I immediately rechristened them. So RPB is really peculiar Buck. And all of us who knew and loved Dick know that he really could be really peculiar. R.W. Murray is rather weird. C.N. Reilley, Cyanide Reilley. So I thank them for giving me such an outstanding grounding in electrochemistry, but most of the thanks, of course, goes to the group. Jeremy Pittcon, who's worked with the titania and the photoanodes, and then the ruthenia and platinum on titanium. Jeff Long, who's got his fingers in everything. Chris Chervin, who's really been working out the nature of these ruthenia nanoskins. Many of the micrographs came from our collaboration with Rhonda Stroud. The manganese oxide proton wire was worked out by Mike Dosher when he postdoced with us, and the oxide ion transport wire at 600 degrees C was worked out by Christelle Liberty-Robert when she did a 2.5-year sabbatic visit with us. And I thank again my excellent nanoarchitectural firm and you for your attention.
We have so many people in the line, so we have a good distribution for any questions. Don't be polite. Yeah.
I'd like to know for those silica, for the ruthenium oxide, taking away the hydrogen stuff, how stable are those materials?
When there's so little ruthenia there's about 300 micrograms per square of the paper, that if you heat it too high or you give it that reducing atmosphere that converts it to metal, you break the wire. You change the morphology. So it's not going to be stable under hydrogen. But so far it's been stable at least at room temperature under argon and in the presence of methanol. We have to now look at that as how stable is it up at 90 degrees C where you'd be running a methanol fuel cell. But it does seem to be helped to be in condensed medium, like in the electrolyte. That does seem to convert some stability to the film. George.
If you ignore the mechanics of how fragile you can make things, electrically, how much surface area or porosity or whatever you want to use could you get with your ruthenium oxide and still let it function the way it does?
Well, in the silica aerogels, it was relatively robust. We modified the scaffold process such that we could actually drop the silica aerogel and it would bounce. So we strengthened the neck regions between the particles, and that makes it a very elastic type of system, so it's much more robust, but still too painful to make. And in that case, then you're just covering about 1% to 2% of the surface area with the ruthenia. The interesting point is when the fibers that the ruthenia is deposited on are 10 nanometers, the object geometric normalized capacitance, I'm not saying anything about the innate conductivity of the ruthenia, but what the object gives you if you use it as an electrode is about 0.5 millisiemens per centimeter. When we put it as a shell on the paper on fibers that are about 1,000 times thicker, the object conductivity, again, geometric factor normalized, is 1,000 times higher at half a Siemen per centimeter. So to me, that's very encouraging. That means we may be able to amplify the conductivity of these nano shell type coatings, not just for ruthenia, which gives you more performance on our length scale as opposed to the no current that flows when you've just got a nanowire.
I think in the interest of staying on time, we'll quit right now. Thank you very much.
Thank you.
Yeah.